For nearly 20 years, Arctic winter sea ice appeared to be doing something unexpected. Despite rising global temperatures, the amount of ice covering the Arctic Ocean at the end of winter was no longer falling as quickly as it had before. Some people saw this as evidence that the Arctic was beginning to stabilize. Others claimed climate models had exaggerated the danger. But scientists studying the ice warned that the apparent pause was probably temporary. Now, new satellite measurements suggest that warning was correct. Between the winter peaks of 2024 and 2025, Arctic sea ice extent fell by 5.8%. It was the largest year-to-year winter decline observed since continuous satellite records began in 1978. The ice recovered slightly in 2026, but its maximum extent remained the second lowest in the record. According to a new analysis, the long-term winter decline has returned, and the Arctic's brief period of relative stability is over. Every winter, darkness spreads across the far north and the surface of the Arctic Ocean freezes. The ice expands for months until it reaches its annual maximum, usually in March. Then sunlight returns, temperatures rise, and the ice retreats toward its September minimum. Scientists monitor both seasons because they reveal different parts of the Arctic climate system. Summer sea ice receives the most attention because it has declined dramatically over recent decades. Winter ice, however, is equally important. It determines how much frozen area exists before the melting season begins. When the Arctic enters spring with less ice or with thinner and younger ice, it becomes more vulnerable to warm air, ocean currents, storms, and sunlight during summer. Satellite observations show a clear long-term decline in Arctic sea ice. Yet between roughly 2005 and 2024, the winter maximum did not fall as rapidly as expected. The decline seemed to slow, even while greenhouse gas concentrations and global temperatures continued rising. This created an apparent contradiction. How could the planet keep warming while the Arctic's winter ice appeared almost stable? The new study argues that the slowdown was not evidence that warming had stopped. Instead, natural variations in ocean and atmospheric circulation temporarily concealed part of the human-driven trend. Currents can move warm water into or away from ice-forming regions. Winds can push ice together, spread it apart, or transport it out of the Arctic. Changes in storms and pressure systems can also influence how much ice forms in a particular winter. For a time, these natural processes favored ice growth in parts of the Arctic and partially offset the effect of a warming climate. But they never removed the underlying pressure. The atmosphere continued trapping more heat, while the ocean continued storing much of that additional energy. When the natural conditions shifted again, the hidden decline reappeared. The sudden loss between 2024 and 2025 was especially striking during the growth and peak phases of the winter season. Instead of reaching an area close to the recent average, the ice stopped expanding earlier and covered substantially less ocean. In March 2025, the annual maximum reached a record low. March 2026 produced another exceptionally small maximum, statistically tied with the previous year in some assessments. A difference of a few percent may sound modest, but the Arctic Ocean is enormous. A 5.8% decline represents the disappearance of ice from an area comparable to a large country. It also happened during winter, when the Arctic should be rebuilding its frozen surface. The event was not simply another low summer minimum caused by seasonal melting. It showed that even the coldest and darkest part of the year was no longer enough to restore the ice to previous levels. Sea ice loss does not directly raise global sea level because the ice is already floating, just as melting ice cubes do not cause a full glass to overflow. Its influence comes through other mechanisms. Bright ice reflects a large portion of incoming sunlight back into space. Dark ocean water absorbs much more energy. When ice retreats, the exposed water warms, making it harder for ice to survive and easier for additional melting to occur. This is known as the ice albedo feedback. It is one reason the Arctic is warming several times faster than the global average. Less ice allows more solar energy to enter the ocean. The warmer ocean delays autumn freezing and can release heat back into the atmosphere. That warmer atmosphere then makes the following ice season more difficult. The age and thickness of the ice also matter. Decades ago, much of the Arctic was covered by multi-year ice that survived several summers. This ice could grow several meters thick and resist temporary periods of warm weather. Today, a much larger share of the Arctic is covered by first-year ice. It forms during autumn and winter, but has never survived a summer. First-year ice is thinner, saltier, and more fragile. Strong winds can break it into smaller pieces, while waves can travel farther into newly opened water and damage the remaining ice from the edges. Even when satellite images show a broad frozen area, that surface may not have the strength or volume of the older Arctic ice it replaced. This difference helps explain why a small recovery in ice extent does not necessarily mean the Arctic is recovering. The 2026 winter maximum was slightly larger than the 2025 maximum, but it remained extremely low. A single colder season can increase the visible area of ice without rebuilding the thick multi-year structure that once dominated the region. True recovery would require a sustained increase in both coverage and thickness over many years. The ecological consequences begin beneath the frozen surface. Sea ice is not an empty platform. Algae grow within and beneath it, providing food for tiny organisms that support fish, seabirds, seals, whales, and polar bears. When the timing of freezing and melting changes, the entire seasonal food cycle can shift. Some species may temporarily benefit from more open water, while others lose the habitat they need to hunt, rest, reproduce, or escape predators. Polar bears rely on sea ice as a platform for hunting seals. Walruses use it for resting between feeding trips. Certain seals create dens and raise their young on or beneath the ice. As stable ice becomes less available, animals may travel farther, spend more time on land, or compete for smaller areas of suitable habitat. The transformation also affects people. Arctic communities have used predictable sea ice for travel, hunting, and cultural traditions for generations. Thinner ice can become dangerous even when it appears solid from above. Routes that once remained reliable for months may open earlier, freeze later, or fracture suddenly. At the same time, declining ice is opening longer shipping seasons. Vessels can travel through routes that were once blocked for most of the year. This may shorten journeys between parts of Europe and Asia, but it also brings noise, pollution, accident risks, and greater industrial activity into one of Earth's most sensitive regions. More ships can disturb wildlife and introduce soot that darkens snow and ice, helping them absorb additional sunlight. Scientists are also studying whether changes in Arctic sea ice influence weather farther south. The Arctic and the middle latitudes are connected through the atmosphere and ocean. Large changes in temperature differences may affect winds, storm tracks, and pressure patterns. Researchers continue debating the strength of particular connections, and no single cold spell or heat wave can be blamed entirely on missing Arctic ice. But the loss is large enough to alter one of the major components of Earth's climate system. The new study does not mean the Arctic will now lose the same amount of winter ice every year. Sea ice naturally varies. Some winters will be colder, others warmer. Winds and currents may produce temporary increases, just as they helped create the earlier slowdown. The important finding is that short periods of stability should not be mistaken for a reversal of the long-term trend. Climate systems rarely change in smooth, predictable lines. A graph may flatten for several years and then fall sharply. Natural variability can temporarily hide warming or amplify it. This is why scientists rely on decades of observations, not one season, when identifying major changes. The satellite record now extends for almost half a century. Across that period, the direction is clear. Arctic sea ice is shrinking, becoming younger and becoming thinner. The record low winters of 2025 and 2026 show that the region is entering the melting season with less protection than it once had. The Arctic's apparent pause was never a return to normal. It was a temporary balance between natural circulation patterns and a warming planet. That balance has now shifted. The ice is declining again, and the ocean beneath it has continued accumulating heat. What happens next will depend partly on year-to-year weather, but the long-term future depends on how much additional greenhouse gas enters the atmosphere. The Arctic may still surprise scientists with occasional cold winters or short-lived recoveries. Yet those fluctuations cannot rebuild decades of lost ice by themselves. The warning from the latest measurements is not that the Arctic suddenly changed in a single year. It is that the change never truly stopped. For a while, natural forces hid part of it. Now the decline has become visible again, and the frozen roof of the planet is entering a new and increasingly uncertain phase.